Good morning, class. We are looking at practice test number 4, module 4, chapters 8 and 9. And here's chapter 9, inferences from two samples. So in short, what did we do in chapter 8? We did the test of hypothesis for one sample. Now we do the same thing. In this case, we are dealing with two samples. Number one, among 843 smoking employees of hospitals with the smoking ban, 56 quit smoking 1 year after the ban. Among 703 smoking employees from workplace without the smoking ban, 27 quit smoking a year after the ban. Is there a significant difference between the two proportions? Use 0.01 significance level. There's a proportion, but the difference between this and previous chapter is that we have two groups. And so what is given? That's the first thing that we have to make a note of, and that is extremely important, everybody. So the first group, the sample size, N is 843, and out of those X, 56 quit. Now, because we have two groups, instead of N, we're going to call it N sub 1. Instead of X, we're going to call it X sub 1. And in this case, the second group, we call this N sub 2 and X sub 2, and we are dealing with the BD binomial distribution. Now, we all remember P hat was X over N. So in this case, P1 hat would be X1 over N1, P2 hat would be X2 over N2, and so forth. We also have something called P bar, which is X sub 1 plus X sub 2 over N sub 1 plus N sub 2. And the z-score, the test statistic for a case like this, again, in your formula sheet, you can find that is P1 hat minus P2 hat over the square root of P bar Q bar over N1 plus P bar Q bar over N2. In essence, P bar, the pulled proportion. All right, so as I mentioned, P1 hat is X sub 1 over N sub 1, so 56 over 843. P2 hat would be X sub 2 over N sub 2, 27 over 703. And of course, and by the way, alpha was, of course, 0.01. So it's important to write the given and take it from there. And now, having this formula, this P bar is X sub 156 plus X sub 227. So you're going to add them up and then divide it by N1 plus N2. And of course, as a P is 1 minus Q, Q bar is 1 minus P bar as well. Q bar is 1 minus P, just like the rest of it. All right, and so let's go with test of hypothesis. The first step, we have to write H0 and H1. H0 is P1 minus P2 equals 0 because we have two groups. Proportion number 1 minus proportion number 2 for the second group is equal to 0. We go with the equality. Now over here, we write the same thing, either less than, greater than, or not equal. There are three signs we use for the second part. Which one? We have to read and figure out, is there a significant difference? It doesn't mean less than, it doesn't mean greater than, it means if there is a difference, that means not equal to. So there are three signs that we use for the second part. Not equal to, less than, and greater than. And as you read this, it says we have to use not equal to, which is going to be the claim. And so this is the claim. And then class, this is the two-tailed test. This is the left tail test. is the right tail test. So H1, P1 minus P2 is not equal to 0. It's a two-tail test and it's a claim. So what I'm telling you is that the process is identical to what we did in chapter 8. The formulas are different. Okay. So the second step is to calculate the test statistic. P1 hat is equals P1 hat. That's why we did the calculation. Minus P2 hat over the square root of P bar Q bar, P bar Q bar, the product of these two over N1 and then over N2. So this is the second part. Let me erase my work. And so that's the test statistic following this formula. Again, write the formula, plug. The next step is the critical value comes from the choice of alpha. Alpha is 0.01 using the table technology. Okay, and this becomes 2.4319, by the way. And the critical value comes from the choice of alpha, which makes it plus minus 2.575. Why is that the case? It's a two-tail test. That means 0.01 divided by 2 on each side. Okay, 0.005. That's the meaning of it. So in order to make a decision, we're going to go with the drawing. And here's the drawing, everybody. So you have your distribution. The critical value of negative 2.575 here. This is the tail on the left side. The critical value of positive 2.575 is here. And this is the tail. Now, this number is the test statistic. You have to locate that. This is somewhere here. Again, it may not be to scale, but it doesn't matter. The two tails are where we reject H0, but it's in between, way into the non-rejection region. So the decision is only about H0 after we do all the calculation. Fail to reject the null hypothesis. Again, look at the location. And now we expand to the second part and the third part. The second part and the third. The second one is the claim true or false? Well, if we are not rejecting H0, that means we are rejecting H1. That means we are rejecting the claim. That means the claim is false. And now we reinstate as follows. There is not a significant difference between the two proportions, because that was the question. Now, as far as, and I'm going to go over the p-value right here, and as far as the p-value is concerned, we can use the tabular technology. The p-value is this. If it was a right tail test, would be the area to the right of test statistic. This area, everybody. This area. But it's not a right tail test. It's a two tail test. So you have to multiply this by 2 and compare it to alpha. That's how you do that if you're doing it using a table. Find the area to the right of test statistic 2.4319 and then multiplied by 2. Now, what about the calculator? If for any technology, for example, a TI calculator, you go with TI calculator and use two proportion z-test, which means stat test, two proportion test, enter data or stats, N1, N2, X sub 1, X sub 2. So take a look at what happens here. So again, so X sub 1, N sub 1, X sub 2, N sub 2. We have those numbers, we put them here. Now, which one do we use? Two tail test, less than or greater than, left tail test, right tail test. We use a two tail test. And it gives us some numbers. Let's see what it has given us. Number one, these are the three items that we are interested in. And as you're looking at those items, just to give you what has been calculated, this one is P1 hat. This one is P2 hat. This one is P bar. Take a look at those three values. This one, P1 hat. This one, P2 hat. This one, P bar. So it has done a lot of calculations. One more thing. This is the p-value. That means this area times 2 because it's a two-tailed test. P-value in a matter of comparison to alpha of 0.01, it's either smaller or larger. Because it's larger, fail to reject the null hypothesis. Same decision. That's how the p-value works, everybody. All right, we are going to continue with the same question, and here's the part that we are adding, part B. Construct the 99% confidence interval for the difference between the two proportions. Now, I want to make sure we understand this concept if we want to compare this to the first part, the test of hypothesis. This is the information we have from the previous page. Take a look at alpha. If you have a two-tailed test, the confidence to correspond to this must be 1 minus that. If it's a one-tailed test, doesn't matter left tail test or right tail test, you have to multiply this one by 2 and subtract from 1. For example, if this was a left tail test, that means 98% confidence interval would be equivalent to that. And I hope everybody's following the concept. So first, we want 99% confidence interval. Second, I wrote all the information we gathered from the previous page and everything that you have here. And now we are going to use the formula. Everybody remembers that for one sample was P hat plus minus E. It's similar to that P1 minus P2 hat plus minus P1 minus P2 hat minus E and plus. That means P1 minus P2 is between the two. That's the meaning of it, everybody. And so, having said that, what is the formula for the E? Z alpha over 2 squared of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. And I hope you remember for one sample, or you can look at the formula sheet was Z alpha over 2 squared of P hat Q hat over N. So it's similar to that. So we have all the information here. We are going to plug in. What about the Z? Because it is alpha equal to 0.01 and it's a two-tailed test and this is a 99% confidence. If you look up the table, it gives you exactly the same Z. Even the Z is given here, 2.575. Let's plug in. You do the math, you go through the process, a bunch of decimals, you end up with 0.0289. I'm showing you the intermediate steps, but the idea is to understand the formula and then we plug in. Now, P1 hat minus P2 hat is the difference between the two numbers. Now, notice what I have here versus what I wrote here. I want to use more decimals here. Remember, ultimately at the end, you can do the rounding. So it gives you a better idea. So you have this number, and now you are going to subtract this number from it and add to it. There are two ways to report a confidence interval. They may want you to write it as P1 hat minus P2 hat plus minus E. So that means this one plus minus this one, and you're done. Or they may want you to report it in this fashion. And that means P1 minus P2 is between these two numbers, negative 0.000878 and positive 0.056922. Now, this is a very important statement. Because the confidence interval limits, what is it? One of them is negative, one of them is positive. Contains zero. So we do have number zero in between. There is not a significant difference between the two proportions. That means fail to reject the null hypothesis. If both of them are negative, in essence, it's like a left tail test. If both of them are positive, it's like a right tail test. Okay. So you may or may not, you have to, uh, you know, reject the null hypothesis. You have to look at the question, but that is important to understand. Number zero is in between. Now, let's do this by technology. We are going to go with confidence interval, two proportion stat test, two proportion z interval plug-in. So two proportion z interval, we put x of 1, n sub 1, x of 2, n sub 2, and we want a 99% confidence interval. And it gives us this, and take a look at what we are given here and what we are given here. I'm going to start with the right side, 0.0569. That's very good. Of course, if you stop here, then you have to change this to 0 and this one to 7. But if you stop here, this changes to 7, this changes to 7. And what is this one? I want to make sure, again, everybody knows the meaning of this number. This number means minus 9 times 10 to the power of minus 4. This is a scientific notation, which means put the decimal here. You have to move it 4 places to the left, which is very close to this value that is done here. So this is done by technology. This is done by table, but the numbers are extremely close, as you can see. Okay. We see the two are almost identical. All right. Here's the second question. Company A claims that its yogurt cups contain, on average, fewer calories than that of a competitor. A sample of 50 such yogurt cups of Company A produced an average of 141 calories per cup with a standard deviation of 5.4 calories. A sample of 40 yogurt cups from a rival company, B, produced an average of 144 calories per cup with a standard deviation of 6.3 calories. If the calories of the yogurt cups for company A and company B have different variances, use a 0.01 significance level to test the claim. I want to mention this concept. The type of formula that is used for this test of hypothesis depends whether or not we are dealing with different variances or not. Generally speaking, if we don't have any information, we are going to assume different variances. In some cases, we may not, and I'm going to look at that case also. But that's important to understand. This is almost always given, okay? Now, so what is the given? So I'm going to write NXS company A, company B, okay? So N for the first company is 50, for the second company is 40. So N1, so N becomes N1, for the first one is 50, N2 is 40. Now by X, I mean X bar. X bar for the first one is 141, that means X1 bar, and X2 bar is 144. And S, the standard deviation for the first one, S1 is 5.4, S2 is 6.3, and alpha is 0.01. So that has got to do with understanding how to write the given. Okay, we are going to move on. H0 mu1 equals to mu2. There are two ways to write this. You can write mu1, let me write it at top. Mu1 equals mu2, or you can write mu1 minus mu2 equals 0. It depends on how they want you to write it. Both mean the same thing. But be consistent when you do the writing. Now, H1, if you go with this one, mu1 and mu2, okay? So what are we checking to test the claim? What is the claim? Company A claims that its yogurt cups contain on average what? Fewer calories. So mu1 is less than mu2. That is the claim, and that's a left tail test. So H1, mu1 is less than mu2 because of this statement, and that is the claim, and that's a left tail test. By the way, for some reason, if the claim is not given, you choose which one is the claim, and then you work on it. If we were to write it in this fashion, the second part would become mu1 minus mu2 less than 0. Okay, and of course, that means the same. The next one is to calculate the test statistic. And the test statistic, T, is x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. Again, that one is in the formula sheet. And so plug in. By the way, as far as the formula is concerned, the reason I have a 0 here, in many texts over here is really is minus. So the formula, and I'm going to write the formula really is x1 bar minus x2 bar in a parentheses. The denominator is the same thing. S1 squared over n1 plus s2 squared over n2. And then it's minus mu1 minus mu2. And this comes from H0, and it's always, always 0. That's why I put it. And the reason I put that, because there are cases out there with the application that they may not claim it to be equal, but it is, for example, less than that by precisely a number 2, for example, calories. So it doesn't have to be 0, but for our case, will always be 0. That's why I put that on. So that's the formula that is used. And if you plug in, you get this number. Let me erase my work. And now the next step is to use the critical value. And to do so, alpha is 0.01. What about degrees of freedom? With the limitation of a table and doing it by hand, the degrees of freedom is smaller of the two, n1 minus 1, n2 minus 1. So alpha is 0.01. For a case where we use different variances, and if we are doing it without the technology, because degrees of freedom can be calculated with the technology, which is a pretty complicated formula, I'll go over that in a moment, and then we put n1 minus 1 or n2 minus 1, which makes it 50 minus 1 versus 40 minus 1. And obviously 40 minus 1 is smaller, so we go with 39. And now from the table, we get negative 2.426. Alpha is 0.01. Why is it negative? Because it's a left tail test. Now let's put all of that into a graph. So here's what we have. With alpha of 0.01, degrees of freedom of 39, the critical value T is negative 2.426. Where do we put the test statistic of negative 2.3901? Somewhere here. Again, this is not to scale by any means, but it's way into the non-rejection region. The tail, the left tail is the rejection region. Okay? They call this the rejection region, RR. And here not NR. And so with that the case, you can see this is way into the non-rejection region. Don't reject H0 or fail to reject. Normally, they don't use the expression do not. They say fail, okay, to reject H0. All right. So if we are not rejecting H0, what are we rejecting? H1. If you're rejecting H1, then you're rejecting the claim. That means the claim is false. And now you reiterate and reinstate what happened. There is not enough evidence to support the claim that company A's yogurt cups contain on average less calories than that of its competitors. This is to make sure we understand what this thing means. But all the calculations result in the first part, okay? All right. So we are looking at the same question. We want to calculate the p-value for the test of the previous part and reminding everyone that it was a left tail test. So it is the area to the left of the test statistic. So this is your test statistic. So this is the area. The area to the left of that, and you use technology table and so on. And obviously, again, so in the case of a p-value, you're comparing two areas, the area which is known as the p-value and the area which is known as the alpha, okay? So having said that, because it's a left tail test, area to the left of the test statistics t equals negative 2.3901 is of interest to us. Now, if we are doing this mostly, we will do that with the technology. But what happens if you're doing the table? I want to make sure everybody understands how it works with the table. We are looking for the degrees of freedom of 39. So we go on the left column and we locate number 39. And now we want to locate this one. And remember, it doesn't matter positive or negative as far as the way you read it. It's given with positive. For the left tail test, you make it negative. So you're looking for this number, let's say positive 2.3901. And as you look at these numbers, we don't have it, but we do recognize that this number, positive one, is between these two. So this is degrees of freedom 39. And this is their number that contains, so negative 2.3901 is between negative 2.426 and negative 2.023. Positive is between the positive. And therefore, the area is also between these two numbers. So the area in one tail, because it was a left tail test, is between these two numbers. And this p-value is larger than 0.01 and less than 0.025, clearly larger than 0.01, and you have the same decision, fail to reject the null hypothesis. Therefore, the claim is false. Decision is in agreement with the previous point. Now, what I want to explain is what happens if you use technology. But again, you need to understand what's given. You need to understand what formulas are used. So you go with two sample t-test, okay? And that means stat test, two sample t-test, and you enter x1 bar, s1, n1, x2 bar, and so on. You put all the information, and this is less than. N1 is 50. There is a typo here. Okay. and it will give you the result. Take a look at what happens here. Calculated results are different since degrees of freedom has a different value. Take a look at the degrees of freedom. Degrees of freedom is 77.111. Why is that? It has a very complicated formula. A plus B quantity squared over A squared over n minus 1 plus B squared over n2 minus 1, where A is S1 squared over n1 and B is S2 squared over n2. That's why we don't use that formula. It's pretty complicated. And normally, when we use smaller of the two, the result is very close. You'll see it in another example that I do that. So in this case, the p-value, so this is degrees of freedom, okay? And the p-value is this number, 0.00964, which is clearly less than alpha of 0.01, and you reject H0. So we do get a different answer here. All right, we want to find the 98% confidence interval for the difference between the two means. And this is the information we found in the previous page, and I want to show you why we need that. As you recall, the confidence interval for the mean was x bar plus minus e. Now it's x1 bar minus x2 bar plus minus. And so we need to calculate the E. The E has the following formula. E is T alpha over 2 square root of S1 squared over N1 plus S2 squared over N2. Now, here's what I want you to understand. Alpha was 0.01, and it was a left tail test. And in essence, it was a one tail test. So if you multiply that by 2, subtract it from 1, you get 98%. So they correspond to each other. That's why you have the same T here. Okay, so the T comes from here, so we put 2.426 here. What about this one? Notice this is identical to the denominator here. That's why I wrote the test statistic as the numerator -3, denominator 1255169. I don't have to recalculate anything. Or look up the T. I already have the T. I already have the denominator, which is identical to that. I use that and I come up with the value of. So I hope you see how easily you can do this calculation. Now, x1 bar minus x2 bar plus minus 3. What is x1 bar minus x2 bar? The numerator is that, x1 bar minus x2 bar. So minus 3 plus minus this number. So this is one way to report it. Another way of reporting, you're going to say mu1 minus mu2 is between these two numbers. And again, it contains 0 because it goes from negative to positive. Because the confidence interval limits contain 0, there is no significant difference between the two means. Fail to reject the null hypothesis. So this corresponds to what we just did. Now, let's go with the TI calculator. And when we plugged in, the question that they're going to ask, by the way, are you going to pull it? The answer is no. That's why those difference variances come to work here. So you put everything, including the C level, confidence level of 0.98. Okay, and pulled no. And this is the number that we get. And why is it different? Again, the degrees of freedom is different, but it is consistent with what we did with the calculator for the previous page. Okay, and note calculator results are different since these degrees of freedom has a different value. And of course, because the confidence interval limits are both negative, and see, both this is minus 5.982, this is minus 0.08181. Both of them are negative. Now, pay attention to this. Because the confidence interval limits are both negative and do not contain 0, there is a significant difference between the two means. Reject the null hypothesis. That's the difference between the two. 0 is in between, fail to reject the null hypothesis. 0 is not, reject the null hypothesis. Now we're going to look at exactly the same situation, but we are going to assume equal variances because I want to show you that a different formula is used. And by the way, don't assume that unless they say so. In which case, we have the same H0, we have the same H1. So what is the difference? Well, test statistic uses a different formula, slightly different. T equals x1 bar minus x2 bar over the square root of sp squared over n1 plus sp squared over n2. That's why in this case we use the fold variance, the average in essence. And the formula is that n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 minus 1 plus n2 minus 1. That is p squared. So you calculate that. That's why the given is handy. And we have the value. Now we are ready for the test statistic. The numerator remains the same as before. The difference between the two was -3. And we end up with this. And again, that 0 is the same thing because it comes from H0. -2.4316. Critical value, alpha is 0.01. Degrees of freedom, the way it works here, and it gives us the same result with the technology, is that we add up the degrees of freedom. So in other words, 50 minus 1 and 40 minus 1, they will be added. So degrees of freedom is n1 minus 1 plus n2 minus 1, which gives us 88. Now, what happens again if you are going to use a table, limitation of a table, if you don't have 88, then you have to choose the closest number that the table gives you. And in that case, we are going to go with 90. Okay, so when using the t-table, if you're using technology, you don't have to worry about that. Make sure you give it 88, not 90. This is for the sake of table and its limitation. And so t is -2.368. And now we are going to do the drawing. As you can see here, the critical value is -2.368. The test statistic is -2.4316, which is smaller than that. That puts us way into the rejection region. Therefore, reject H0. So reject H0 because the value of the test statistic is inside the rejection region. So if you're rejecting H0, let's go back here. If you're rejecting H0, you're accepting H1, which makes the claim a true statement. So claim is true. What does it mean? There is sufficient evidence to support the claim that Company A's yogurt cups contain on average less calories than that of its competitors. So again, equal variances gives you a different formula for test statistic, different value for the degrees of freedom. Now we're going to continue with the same question. We're going to calculate the p-value. The p-value, again, this was a left tail test, is the area to the left of, this is your test statistic, this area, everybody. Area to the left of test statistic, degrees of freedom, we are choosing 90, okay? So test, degrees of freedom, we are choosing 90. And as you can see here, we don't have the value of test statistic. And we compare what we have here, because again, you have to compare the two numbers when they're positive because of the limitation of the table. And 2.4316 is less than 2.368. And so the p-value is between the two. And if the p-value is less than 0.01, that's what matters, and that happened to be alpha, we get to the same decision, which is rejecting H0. P-value is less than alpha of 0.01, same decision as part A, reject H0. Now, let's look at the technology. We use two-sample t-test. And when we go through the process, it says pulled, we say yes. So you put the information in, X1 bar, S1, so on and so forth. And over here where it says pulled, you say yes. You calculate. This is the information it gives you. So take a look at what is important to us. Degrees of freedom is 88, as we mentioned. And again, the reason we used 90 class, the limitation of the table. There may be tables online that they don't have this limitation, okay? But because of that, we went with number 90. We had no choice. Over here, the calculation there doesn't have a limitation. Degrees of freedom is 88. And what is this? This is the p-value, which is anyways less than alpha of 0.01. And it gives us the same decision, everybody. We're looking at the same question. Part C is asking for 98% confidence interval. Because it's a one-tail test, doesn't matter left or right. Alpha 0.01 times 2, 1 minus that. So they correspond to each other. So you use the same thing here. And so degrees of freedom is 88, but using a table, we go with 90. Remember that. And so x1 bar minus x2 bar plus minus e. Again, look at the formula. This part, you really don't have to calculate. Again, I'm going to remind you that when we calculated the test statistic in the previous page was negative 3 over 1.23376, and this was the answer. So we have this part. And what about the t? We have the critical value, again, that we looked up. Remember that? And so 2.36. My point being, you don't have to do a lot of work. You can use the previous work here. So the product of the two is and this is this one. This is this one. And here's the product. Now, x1 bar minus x2 bar is negative 3 plus minus e plus minus 2.9216. This is one way to report it. So you report it just the way they want it. Or mu1 minus mu2 is between the two numbers. Minus 3 minus this number and minus 3 plus this number. And obviously, when you look at both ends, they are both negative. They do not contain 0. Because the confidence interval limits do not contain zero, and that's the key. There's a significant difference between the two means. That means reject the null hypothesis. Reject the null hypothesis. As far as technology is concerned, if we want to go with the technology, two sample t interval, stat test two sample t interval, and we pull it, yes, and it gives you all the information. Look at the information that we get. What is this? The p-value. If you look at this, the confidence interval, minus 5.923, extremely close, minus 0.0766, minus 0.0784, extremely close. So again, the main difference here is because the degrees of freedom, we have to go with 90, they go with 88. They don't have that limitation, okay? As you can see, very close. Number 4, test a claim that weights of a male college students have a larger variance than female college students. Use a significance level of 0.05 and assume the populations are normal. So alpha is 0.05. So what do we use when we want to look at a difference of, a case like this involving uh, two groups, and we are discussing the variation. That means sigma 1 versus sigma 2, or sigma 1 squared versus sigma 2 squared. Okay, what do? We use what's called the F test, which looks like that. For the comparison of two variances or standard deviation, an F test is used. The F test should not be confused with the chi-square test, which compares a single sample variance to a specific population variance. So chi-square, you have that and you compare it with a number. In this case, you have two different groups. Characteristics. Number 1, the value of F cannot be negative again, just like chi-square has to be positive, because variances are always positive or zero. The distribution is positively skewed. The mean value of F is approximately equal to 1. The F distribution is a family of curves based on the degrees of freedom of the variance of the numerator and the degrees of freedom of the variance of the denominator. Now we have two degrees of freedom, one for the numerator, one for the denominator, because F is calculated as S1 squared over S2 squared. Now, always you choose the one which has a larger variance or standard deviation as the first group. So this F must always be larger than 1 because of the limitation again. Otherwise, you're wrong. So the way you choose, so it doesn't matter how they give it to you. The one that is larger, you put it at top as the first group. In most cases, unless otherwise mentioned, the F test has two terms for the degrees of freedom, that of the numerator n1 minus 1 and the denominator n2 minus 1. Again, n1, even if it's a different order, the one with the larger value of standard deviation or variance is the first group. Always remember that. So the F table for alpha equals 0.05. We have a F test for different alphas. So the very first thing you look for, if you're using a table, choose the alpha because they have it for alpha 0.0 equals 0.05, or otherwise, for example, alpha equals 0.01. Then you need that one, degrees of freedom. DF1, that means degrees of freedom of the numerator, you see at top. DF2, degrees of freedom of the denominator, you have it on the left column and you bring them together. That's how you do the reading. So first you have to have an alpha because they have different tables. Then degrees of freedom of the numerator, we call it DF1, is at top row. Degrees of freedom of the denominator is at the left column. So I'm going to continue with this question. And this is the information given symbolically. N is 31, X bar is 168, S is 28. That's for females. Now, before we move on, we know we are going to use the F test where, by the way, test statistic is S1 squared over S2 squared. You have to figure out on your own which group is the top group, is the first group, the one which has a larger variance. Look at S. Because S equals 28 is larger than S equals 25, this is your first group. Okay? So we are going to write normal distribution because they said so. Alpha is 0.01. Males, now we're going to write N1 and S1. For females, we're going to write N2 and S2. So first pay attention to this. Okay. It so happened the first group has a larger standard deviation. Stick with that. Now, we are going to go with the test of hypothesis that has 4 parts. Take a look at the way we do it. First, I want to read the question one more time. What are we testing? We are testing that the college students, male college students, have a larger variance. Sigma squared is the variance. There are different ways of writing them. And as you do your homework or exam, just pay attention the way they want you to do it. You could use sigma 1 squared. So let me just, those are 3 different types. Sigma 1 squared equals sigma 2 squared for H0. Or write sigma 1 squared over sigma 2 squared equals 1. Or sigma 1 equals sigma 2. You can't use all 3. You have to use one of it. If they give it to you, pay attention to what they are giving it. So, for example, here you want to deal with the standard deviation, but in these 2 cases, you're dealing with the square of that number. Over here, these numbers are squared, 28 squared, 25 squared, because those are variances. Now, H1, you write it accordingly. Now, because we are testing the claim that weights of male college students have a larger variance, we write sigma 1 squared is larger than sigma 2 squared, which makes it a claim, and it's a right tail test. And the rest of them, the same thing. This would be right tail test claim, right tail test claim. In fact, you always have a right tail test in the case of F distribution because of the limitation of a table. That's why you choose the top one to have a larger variance or standard deviation. Step 2, test statistic, is F equal to S1 squared, 28 squared, over S2 squared, 25 squared. And again, if this number you calculate is not larger than 1, you've made a mistake with your choices. Okay? Be very careful. The next step is the critical value, comes from the choice of alpha, which is 0.05, and degrees of freedom of the numerator, so would be 31 minus 1, and the denominator 29 minus 1. So critical value, alpha is 0.05. It's a right tail test, as it should be. Degrees of freedom of a numerator is 31 minus 130. For the denominator, 29 minus 1 is 28. And you use the F table with alpha 0.05. There are different F tables. So having said that, this is the table with alpha 0.05. So up here is the degrees of freedom for the numerator, and we look for 30. I just chose one of them because of the limitation of the space here, but the left column, yeah, a bunch of them. And you put those 2 together, and that results in 1.8687 as the answer. So that is the critical value. To make a decision, we're going to go with the graph. Look at this graph. It's a right tail test. This area is 0.05, and the critical value is F equals 1.8687. Now, what about the test statistic? This number is somewhere here. Doesn't have to be to scale, but way into the non-rejection region. It is the tail that is a rejection region. Way into a non-rejection region, therefore don't reject or fail to reject the null hypothesis because the value of the test statistic falls in the non-rejection region. So now we go back and we read this to make a decision. So fail to reject, if we are not rejecting the null hypothesis, what are we rejecting? H1, the alternative hypothesis, which means that we are uh, rejecting the claim. The claim becomes false. The claim is false, and we rewrite. There is not sufficient evidence to support the claim that weights of male college students have a larger variance than female college students. And if we were to use a technology, we would use two sample F test. And we put the information, and again, I can't emphasize this enough. Make sure S, the one with the larger one, in this case for males, that is S1. So you put it in, and it gives you this information. So look at what it has calculated. It has calculated the test statistic for us, and it has calculated the p-value, of 0.2745, which means, in this case, class, we are looking at the area to the right of test statistic, and the p-value of 0.275 is way larger than alpha of 0.05, we get the same decision, which means fail to reject the null hypothesis. Question number 5, directional asymmetry, or short DA, is a phenomenon whereby a population, one side of each organism is consistently larger than the other, i.e. left larger than right. An evolutionary biologist studying DA measures the length of the left and right wings of his sample of a Drosophila, which is a type of flies whose members are called small fruit flies, collected from nature, and she gets the following data. We have 17 pieces, the length for the left wing and the right wing are reported. Part A, the researcher decides to perform a two-sample t-test to determine whether the mean wing differs between the left and right side of these flies. What type of t-test will she do? Actually, it's mentioned here. I'm going to go over that concept with the alpha 0.05, of course, and then find the 95% confidence interval for the difference between the means. So first and foremost, we are going to use what is called the paired t-test. Okay, so it is a two-sample t-test, but more specifically, it's called a paired t-test. For example, if you look at the case for the result of the average score on the test before and after some sort of a review, it's the same concept. So they are dependent in essence. Okay. And I'm going to go over that in the next page. So it will be explained in the next page. What will be calculated here? Calculate the differences. So in short, all you have to do, calculate the difference. For example, for the first one, you would say 1.34 minus 1.26 and put it here. You get 0.08. For the second one, you would put 1 minus 1.28. You put it here is negative 0.28. That's the difference. And you continue for the rest of them. And you do the one sample t-test on that. That's the bottom line. So that's the difference. These L minus R. By the way, you could use R minus L, makes no difference. And the formulas that follow are very similar to formulas that we see for any x. D bar is summation of d over n. So that means, how do you calculate the average here? Add them up, divide by size. That's the formula. Same thing for the standard deviation. S sub d, the square root of d minus d bar quantity squared over n minus 1, and this is another way of calculating it. Okay. The TI calculator uses stat, edit, clear list, L1 and L2. So the best course of action is to put this list as well as this list into a calculator. Let the calculator do the job for D bar. That means add them up, divide by how many we have, 17. So n is 17. And the standard deviation. Nobody expects you to do this by hand, but everybody expects you to understand which formula is being used. And so in L1, you put this group, in L2, you put this group, and then you work for stats L1 minus L2. And of course, you can work on L3 now because you're going to send this to L3. And here's the result with a bunch of decimals. So what is a paired t-test? Let's discuss. Two means two dependent samples known as matched pairs. Key concept. Testing hypotheses and constructing confidence interval involving the mean of the difference of the values from two populations that are dependent in the sense that the data consist of matched pairs. That's the meaning of it. The pairs must be matched according to some relationship, such as before and after measurement from the same subject, or in this case, the left and right. Good experimental design. When designing an experiment or planning an observational study using dependent samples with matched pairs is generally better than using two independent samples. Hypothesis test. Use the differences from two dependent samples, matched pairs, to test a claim about the mean of the population of all such differences. Number two, confidence interval. Use the differences from two dependent samples, matched pairs, to construct a confidence interval estimate of the mean of the population of all such differences. D represents individual difference between the two values in a single matched pair. For example, the first group that I showed you. Mu sub D, mean value of the difference D for the population of all matched pairs of data. D bar, mean value of the difference, says D for the paired sample data. This is for the population. This is for the sample. S sub D, standard deviation of the difference, says D for the paired sample data. N, number of pairs of sample data. I think the variables are obvious and what they represent. When the values are dependent, do a t-test on the differences. That's the bottom line. And denote the differences with the symbol of lowercase t or capital D. I'm using both of them just to make a point that in some texts they use lower, in some texts they use upper case. Makes no difference. It means the same thing. The mean of the population differences with mu of sub d or mu of capital D, sub D, and the sample standard deviation S sub D or S sub D, the lowercase or uppercase. So degrees of freedom is n minus 1. Use either lowercase d or capital D. And here's the formulas. Now, what I want to discuss, the T, I hope you remember the T for a sample mean was X bar minus mu over S over square root of n. In essence, it's really the same thing here. For the confidence interval was X bar plus minus E, so D bar plus minus. And E was T S over square root of N, is the same thing here. Of course, in this case, S sub K. So that is, in essence, using the t-test on the last column, which was the difference. So we are going to continue and work on that. So this is the same question. We are going to do the test of hypothesis That's the first part that is being done. So H0 mu sub D equals 0. That's the notation we use for the population. For H1, mu sub D is what? It just differs. So the researchers decide to perform the two sample t-test to determine whether the mean wings differs. It doesn't say less than or greater than. So it's not equal to 0. That's the claim, and that's a two-tailed test. This part that we write claim and two-tailed test is extremely important to understand the concept. Now, test statistic, you just use this formula and plug in, again, on purpose. I'm using lowercase d as well as uppercase d on purpose, so everybody can see. We can use both of them depending upon the text. Plug in, and again, this part comes from the uh, H0, and it's always 0. That's why in some text you don't even see that. So plug in, and the result is negative 1.636. The next one is the critical value, which comes from the choice of alpha. Alpha is 0.05. Degrees of freedom is n minus 1, or 17 minus 1. And if you use the table, because it's a two-tailed test, you get plus minus 2.120. To make a decision, we're going to go with the graph. And as you can see from the graph, the critical value of negative 2.120 is here. The positive is here. And test statistic of negative 1.636 is somewhere here, everybody. It's way into the non-rejection region. So the decision is do not reject H0 or fail to reject H0. Now we go back to the first step. So we are not rejecting H0. What are we rejecting? H1. What are we rejecting? The claim. So the claim is false. And we rewrite. There is not sufficient evidence to support the claim that the mean wing difference differs between the left and right sides of these flights. For this sample, it didn't work. So she cannot conclude that this population possesses DA because the mean lengths of the wings on the left and right sides do not differ significantly. Okay. As far as the calculator is concerned, you can use matched pair t-test, put it in, and calculate it to come up with the result. You can try that with the calculator. I'm just showing you what you can use. And I leave it for you to do so. We continue with part B, find the 95% confidence interval for the difference between the means. And again, this is the information we gathered from the previous one. And because it's a two-tailed test, alpha of 5% is the same as 95% confidence interval. So we have the same T, if you will. So alpha over 2. So this is everybody 95%. Each one is 5% divided by 2. So this is 0.025. This is 0.025. And critical value is the same as before. So we are going to calculate the E, D bar plus minus E, where E is TS over square root of N. So 2.120. S is this one, square root of 17. And that gives us 0.01174. So the answer is D bar, which is negative 0.0906 plus minus this number. That's one way to report it. And the second one is to subtract from it, add to it, and we get mu of D between negative 0.208 and positive 0.268. Notice negative to positive contains 0. Since 0 is contained in the interval, the decision is to not reject the null hypothesis H0 mu sub D equals 0. This is very important to understand how confidence interval and test of hypothesis are related. Again, application in science. You can use a TI calculator process by using the T interval, match per T interval, test, and when you enter, you use L sub 3 and you let it do the calculation for you. All right. An ecologist is concerned with whether pollution entering part of the preserve area is compromising the health and growth of an endangered species of snake. To determine this, he decides to measure the length of a set of mature adults from the polluted area, length measurement from unpolluted, length measure from polluted area, from the polluted area and unpolluted area. The researcher decides to perform a two-sample t-test to determine whether the mean length of this snake differs between these two areas with the alpha of 0.05. As far as alpha is concerned in science, unless it's medicine, it's almost always 0.05, even if it's not mentioned. So let's do the math. Again, we have n equals 15 for this group, n equals 17 for this group. So we have to do some calculation, and to do so, we are going to assume different variances. You always assume different variances unless they mention that you have to use equal variances if you go back to the beginning that we did. So sample standard deviation, mean sample size. And of course, n is 15 for this group, 24 for this group. So N1 is 15, N2 is 17. What is the mean? Add them up, divide by 15 for this group. This one, add them up, divide by 24. So I'm going to write the formula for each case. For the mean, okay, you use X bar is summation of X over N. I'm not going to, of course, do that by hand. You use technology. For this one, standard deviation is summation of X minus X bar quantity squared over N minus 1. And you put that into a calculator and you get the following result, which means S1, the first group, X1 bar, the first group, and S2 and X2 bar. And as I said, N sub 1 was 15 here, N sub 2 was 17 here. I think I mentioned 24 by mistake. But in any event, let's erase it. All right, so the first step, H0 mu1 equals mu2, because that's what we are performing, right? Determine whether the mean length of these snakes differ. And so since it says differ, it doesn't say less than or greater than, you have to go with mu1 is not equal to mu2, which makes it a two-tailed test, which makes it a claim. So you want to pay attention to the way they want you to do that. The first one takes the equality always, H0. H1, one of the three, less than, greater than, not equal to. So T is, of course, X1 bar minus X2 bar over S1 squared over N1 plus S2 squared, where N2 under the radical. You just have all of this plug in. And you get 2.8022. The next one, traditional method, we use the critical value with the choice of alpha of 0.05 degrees of freedom. The limitation for the table, we go with the smaller of the two, N1 minus 1 versus N2 minus 1. Now, this one would be 14, 15 minus 1. This would be 17 minus 1, 16. So that is smaller. We go with degrees of freedom of 14. It's a two-tail test, alpha 0.05, and we get plus minus 2.145. To make a decision, we are going to go with the graph. The graph makes it easy to see. So you have the following, okay? And we have negative 2.145 here, positive 2.145 here as the critical value. Test statistic is 2.8022, larger than the positive value of that. way into the rejection region on the right side. So you write all of those. So because test statistic is way into the rejection of the right side, reject H0. So if you're rejecting H0, loosely put, you're accepting H1. You're accepting the claim is true. And now you do the writing. There is enough evidence to support the claim that the mean, and you just rewrite this, the mean length of these snakes differs in the areas. It is larger in the unpolluted area since test statistic is positive. By the way, this part is with the observation that this is positive. If this was negative, that meant it's small. Now, I want to again discuss the p-value and then the calculator. As far as the p-value class would be the area to the right of test statistic, this one, times 2 because it's not equal to. It's a two-tailed test. Whatever the test statistic is, because test statistic is positive, the area to the right of it. But you have to multiply by 2 because it's a two-tailed test. Now, let's go with the calculator. Two sample t-test, and it results in what you see. Note calculator uses a different degrees of freedom. The degrees of freedom it uses this complicated formula, and take a look at this one. This is the degrees of freedom, but 29. By the way, they always round up. So if you go with the table 29, okay, that gives you the t-value. Take a look at the t-value. So critical value alpha is 0.05, degrees of freedom is 29, round down always. You get plus minus 2.045 from the table. Take a look at this one. Okay, that's what you get here. Okay, and so what about the p-value? Look at the p-value, 0.0089. Let's say if you stop here, you change the 8 to 9. So the p-value, I'm using this one, okay, everybody? This is the p-value, 0.0089 or 0.009, clearly less than alpha of 0.05, which results in the same decision, reject H0, everybody.